Hello everyone, this is the final video in the Mintpy tutorial. This video I'll be explaining you every step by step and what it does, why it does, and what is the result you get it. And this is continuation from how to download data to the end process. This will be a longer video and every detailed step is explained in it. So please do watch everything and then let me know in the comments if you have any queries. So I've selected an area in India where you have this more number of landslides and disasters, that is northeastern part. So from there I have downloaded the data as my area of interest. I have downloaded 15 items or 15 data sets. But according to your research, you can download as many data as available and then you can follow the same procedure. Just for the training, I've downloaded 15, but you can go for more. Now, in the Windows Drive E, I have a Mintpy demo folder in which I have the data. Now I wanted to integrate this with the Ubuntu and then start running everything in Ubuntu. So I'll open Ubuntu. And in the previous videos, I already explained about how to install Ubuntu, WSL, Miniconda, ISE2, and Mintpy. Now we have downloaded the data. Now we just have to link this Ubuntu with Windows, and from there we'll start working on Ubuntu. Before that, what we have to do is this is right now in the Conda environment. Now we wanted to activate the Mintpy environment. So first you go for Conda, activate Mintpy. See, once the Mintpy is activated, you can see the Mintpy here. Now what we need to do is we need to add this drive to the Mintpy folder so that whatever we are working here, it will be shown in the Excel, in the Windows. Okay. So change directory, go to mount, E drive, Mintpy demo. See, now Ubuntu has linked with the Windows. This is what we are doing. Now this is the first command that activates the Conda environment and because it contains ISE2, Mintpy and everything. And all the libraries which are required for the processing are also installed in the Mintpy. So that is where you need to first activate the Mintpy environment. And the second thing is we are linking the project file folder. So if you want to see where your current directory is, you just go for PWD and it will show you in E drive Mintpy demo. Okay. So this is what you get. PW means print the working directory. It will tell us where the current folder or in which folder are we working. Because before we start any processing, it is a good practice that you should understand where you are working. Because if you are working some other and your data is some other place, it will become a mess again. So you have to understand like in which place you are working right now. Now, if you want to see the content of this folder, you just go for ls. Like you see here in the Mintpy demo folder, I have all these 15 files. So it is still showing the same Mintpy demo. And in this, I have all the files. See, I'm keeping both of them parallelly side by side because you'll understand really like what is happening in Ubuntu and what is happening in the um, Windows. Okay, so you have this one. Now, just before that, I just wanted to give you one more introduction about the data. So I think I'm good here, right? So here you see the name S1A IW SNC, and we have this zip format. So S1A indicates the Sentinel-1 satellite data. IW is the interferometric wide swath acquisition, and SLC is the single loop complex. And here 1 HDB means it's a one SLC file with dual polarization, that is VV and VH. And this is the acquisition type and acquisition number. And these are the unique processing and product identifiers. From this, you'll explain, you'll understand. So every central or SLC image will contain the radar signal that is recorded by the satellite. Unlike the optical images, these are complex valued datasets that are preserved both the amplitude and also the phase of the radar signal. Because the phase information is what allows us to measure the millimeter to centimeter scale ground deformation using the interferometric SAR. And if you observe clearly, we are keeping this data in the zip format. We are not extracting it. Why do we keep that in zip format? Is because many users usually think that they need to extract the data and then keep it in folders before processing. For that, we have a top stack workflow. This is not really necessary to extract the data because ISCE2 has the capability to read the Sentinel-1 save files directly from the zip folders. And if you are extracting and keeping, it will occupy more of the space from your system. So keep these files compressed and then let us work on the zip files only. And the most important thing is when you extract, there is a chance for you to delete or you know any kind of modification. So we'll just keep the zip files like that, and ISCE2 will make work with that one. Now there is a specific thing for ISCE2. That means ISCE2 always likes to work in a clean environment. So you need to create proper folders for the raw data, for the DEM file, the orbit, and everything. Then a clean directory or the structure will help in avoiding the confusion. So if you create the SLC, only the SLC files will be in the SLC. If you go for the orbit, only the orbit files will be in the orbit. So this again lets you work more clearly. Now what I'm going to do is I wanted to create the folders. So there are two ways to create. One is I can go to the Windows, right click, view, folder. I can make it as SLC. Okay, this is one. But we are working on Ubuntu. We can directly go for Ubuntu and say mkdir, that means make a directory, and p, that is, see, if I create like this, it is already created. So it will be easy for you to type here and create the folders or whatever the things you need. Again, we go for, we have created the SLC and then we have created the orbits. Now we go for the depth. Now you will see the DEM also. And again, you go for the area of interest. Okay, you got area of interest. Now you go for the um, configuration. That is where you get this configuration files. And then you go for um, one files. This is where you get the files to be running in this directory. And then you go for next um, Mintpy. So here, what are the things you are doing? It will be stored in the Mintpy. And finally, we go for the output. Sorry, we go for output. So I've created SLC, orbits, DEM, AOI, config, run files, Mintpy, output. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So these are the folders you have got created. Now, here I'll explain you why we have created these many folders. SLC contains the original zip files, and orbits folder contains the precise orbits. Just like in the Snap, you go for download the or apply orbit file, then Snap will download the orbit files and it will do the processing. The same way, you are giving everything to ISCE and it will start the processing on its own. So here we have the orbit files and then we have the DEM. This is the place where the digital elevation model is saved because DEM is used to remove the topographic phase, just like in the Snap, you're going for the topographic phase removal, where you are adding the SRTM temp like that. So whatever the digital elevation model you have, you can add this, and then AOI folder will give you the area of interest, like the bounding box or the polygons or whichever things you have specific area of interest that you can add. And in the config, you have all the configurations files that are used for the processing. And in the run files, you have the scripts that are generated during the mm, processing in the ISE2 and Mintpy. And finally, the Mintpy folder contains all the Mintpy configuration files and also the processor outputs. And after that, in the output folder, you'll have the exported GOT formats, figures, and also the final products. Now, this is done. Now, if you want to see what folders are there here, just go for the LS and see. See, you have 1, 2, 3, 4, 5, 6, 7, and SLC 8 are there. Okay, at this point, we haven't started any processing. We just rearranging everything in particular folders so that the software can easily understand and then it can do the whole processing. So, in the beginner mistake, people what do is they extract the images. So, don't do that. And also, don't rename these files. Let them be as it is. So, it would be easy for the software to read and then it will do the processing. And also, you don't mix different kind of acquisition tracks because this is just to ensure that Sentinel-1 scenes belong to the same relative orbit and also the acquisition mode. You shouldn't go for IW or GRD, sorry, SLC, not like that, S1AB, like that. So everything should be in the same format with the same S1A, IW, SLC, 1SDB, and the names like that. And then creating the folders also, you should be like consistent folder names throughout the workflow will avoid the path related errors. So this is what has happened. Now, what we have to do is we need to rearrange these files and then we'll go for the download of the precise orbit files here. So the next command, I'll just clear it out and then I'll show it to you from the next command. So we are here. Now we wanted to move these files into the SNC. These are 15 files, so I can just drag and put in the SNC. But when you're going for hundreds of files, you need to have a shortcut. So what you do is the one thing you will just go for one this and say zip file. So okay, so this is the list of the zip files that I have. Now what I want to do is I want to move these zip files into the SLC folder. So MB is for move and then space star and then go for the zip file and then SLC. Now see here all the data is moved into the SLC folder. So that is how Ubuntu is easier for operation. You just need to know the few commands. So this MV command moves all the files from one location to another location. Here we are moving all the zip files into the SLC directory while preserving their original file names. We are not changing anything. If you want to see, then go for again SLC. Okay. So I can go for ls SLC and see in the SLC folder I have my files like I'm showing you here. Okay. Now what we need to do is if you wanted to know the number of files, because say example you have downloaded 200 or 300 files, and when you have copied, if some files are missing, so you cannot go for manual counting. So what you can do is you just go for ls slc hold in the folder and running, and then I go for the star, and then I go for the zip, and next I go for the slash wc minus 1. See, there's a error here. That is because you like what you are creating here, it should like understand. Okay, so this unexpected argument is minus 1 is found, or you can do one more thing, ls slc minus it's l. See, because I typed it as 1. So these are the things which I'm going to explain to you. If I do any mistake or if I face any problem, the same thing if you're also facing, you can learn from that one. So it is 1, no, but it is L. So here it is showing 15. That means I have 15 files in it SLC. You can open and see here I have 15 items. Okay. So this is how we go for the moving on the files. Now we'll start the apply orbit. That means before doing any processing, we need to download the orbit files for these 15 images. If you are having hundreds of images, SLC will download the orbit files, but it will take some time depending on the speed of your internet. So please be patient and don't interrupt when something stopped or something is not showing, because it takes a lot of time depending on the system configuration. Even systems with higher than 1.5 TB RAM and more, it will take days to do the processing of hundreds of images. So when there is no movement, just leave it like that for say 3 to 4 hours. After that, you can go for stopping or pausing and then restart again. But don't expect the result to be available within 5 to 10 minutes. Now we are going for the orbits download. Now here, sentinel images are organized in the folders. The next step, like I told you, we are going to obtain the precise orbits. This is one of the most important processing steps. So why or what is a precise orbit first, and why do we need it? I'll explain you. So every Sentinel-1 image contains orbit information that is recorded during the acquisition. However, the orbit stored inside the product is called as predicted orbit. After the satellite completes its orbit, European Space Agency or ESA will process the tracking data for multiple ground stations and then compute a much more accurate satellite trajectory. This refined trajectory is called as precise orbit ephemeris or POEORB. So ISE2 uses these orbit files to improve the image co-registration, interferogram accuracy, and phase quality, and also the final deformation measurements. So without accurate orbit information, even perfectly acquired sentinel images can produce a poor interferometric result. I've explained you about this co-registration, interferogram, everything in the previous videos. So in this, I'm explaining you again. If the orbit type is predicted, that means which is coming with the file, it has a lower accuracy. It is not recommended for scientific HR analysis. And there are two kinds of different orbits. One is restituted. It is RESORB. It has a medium accuracy and it is something like it comes within a few hours. But the precise orbit POEORB has the highest accuracy and it will be available after 20 days of acquisition, and it is more recommended for the scientific process. Since our datasets are from very long time, these precise orbits are available after every acquisition. So we are using the POEORB, that means the precise orbits. Now we'll have to know one thing. How does ISE2 know which orbit file to be downloaded? So each Sentinel-1 file contains the acquisition date and time. For example, uh, to the S1A, IW, SLC, 1SDB, 2017, 11, 18, like this. So that is the reason why I'm telling you not to rename your files. Now ISCET reads this information automatically. Then it will search for the ESA orbits or the archive in which this ESA has the orbit for the precise orbit files and their validity period including the acquisition time. So ISCE2 will do the search for the orbits and it will download. So you don't have to manually check the data, go to the site, download and everything. Okay. Now we'll just go to the project folder in which we are here. We're already here. So in the mount E Mintpy demos. So before running any processing command, we have to again see what is our working directory. So just pwd, I mean Mintpy demo. Okay. Now just go for the ls orbits. Okay. So I'm at this. I'm not in the orbit file now, so I'll just go to the orbits folder again. See, this is because orbit files is empty, so that is it is showing like that. If I go for ls slc, see it is showing the list of files available in slc. So because slc contains the file, so it is showing. And here orbit doesn't have anything, so it is showing empty. So what we need to do is we'll okay. So like we are downloading the precise orbit. So what you have to do is go this command for file in slc slc fetch orbit py file. See, now I'll explain you what I did. Here, the first line for file in slc slash zip. Okay. That is because we are telling the Linux to process every Sentinel-1 zip file that is available inside the SLC folder. So here I'm telling the Ubuntu to read all these SLC files, and then second is fetch orbit. That means read these files and fetch the orbit. That means get the orbit data for these files. And this minus I says that it specifies the particular SLC folder. So that means the Linux will, the Ubuntu will read this and it will search for the orbit file and it will download the data. So this minus zero, minus O orbits is, it will tell the ISE to save the file or the orbit file into the orbits folder. Okay. So the loop, it will repeat until every Sentinel-1 acquisition has been processed. It will take some time. We just have to wait. So mm, I'll pause it here and then I'll get back once it is done, or we'll continue with this one. I'm just pausing it and I'll continue again. See, purposefully I've deleted one thing to show you that if this is not happening, what kind of error do you face? So in case if you are running this command and if you see fetch orbit.py command not found, then what we have to do? So what we are doing is, the problem is Linux is only searching for the executable paths in the directories listed in the path environment variable. Here, the top stack directory is not in the path. So when we type this fetch orbit.py, Linux will simply say it is not found. Now, depending on how ISE2 was installed, the top stack utilities may not be available directly from the command line. So if you see the command not found, that doesn't mean uh, it is wrong. Okay, ISCU2 is installed properly. But thing is, we need to tell or we need to direct the Ubuntu to find that path. So for this, what we have to do is we need to um, find the path. So just go for the export uh, path. It's going to, it may look, if it is looking tough in the description, I'll give you the complete set of instructions so that you can follow them. And if you have any error or anything, you can let me know. Then I will explain you everything in detail. So I'll be typing that list now. So this command we are telling export. That means we are updating the environment variable. And then path is the list of directories that Linux will search for the commands. And we are adding the ISCE to top stacks into the directory list. Just like when you are doing in the snap, it will ask you whether do you want this path to be copied in the environment variable. Then we will do that. For the snappy unwrapping also, we'll add this snappy unwrapping into the environment variable. The same way we are adding ISCE to top stacks into this environment variable. Now to verify what we have to do is we go for which fetch orbit or yeah, orbit not vy. See here, now it is showing. That means this fetch orbit is available in home, geoscience Viniconda 3, environments, Mintpy, share ISE2 stacks, and fetch orbit.py. It is available here. Okay. So if you are out of Mintpy also, you'll have this problem. And if you are out of internet also, you'll have this problem. So please make sure that you have all these things. Okay. Now, you wanted to see one thing. I'll also go for one more check because I don't want to get the errors during the orbit download. So I'll go for stack sentinel sentinel not so both of them are here. This is how we have to check everything clearly. Okay. Now we have run both the commands and we found the error. Now we'll go for the fetch orbit. So you just go for this and then enter. See, now here if you see, it's the reference time and it is the Sentinel-1 SLA name and it is asking for the username and password. This is because even ISE2 has to download the data through the credentials. And the most important thing is your credentials are not given to anybody. Okay. So they are safe. So you can use your username and password in this to get the um, orbits. So this is the same credential what you have used for downloading the data from Earth Data Login. That means Alaska ASF when you have downloaded it. Right? So I'm using that one. And see, I've typed the password, but there is no problem. Now I'm just uh, reusing my credentials again. So it is just giving me some error. I'll tell you what this error means, and then I'll again re-enter my username and password. So instead of your app data login, you can go for the Copernicus details, your username and password. Then you get your uh, data downloading here. See, the data is being downloaded here, and I can see the orbit files here 1, 2, 3, 4, 5, 6, 7, 8, like that. One by one, ISE2 will start downloading the data. So this will take some time depending on your internet speed. Okay, so if you see here, the download is completed. I have 15 SLC files and I have 15 orbit files. If you want, you can just go for the LS. See, now we have 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. So now we have downloaded the Sentinel-1 data and then we have downloaded the orbit files. Now we are going for the next important step, upgrading the digital elevation model that is required for the processing by ISE2. Now in this step, we'll be understanding about a depth that is covering entire area of interest. And then we are also saving the DEM in the DEM folder. So we are going to save this in the DEM folder. Now I'll explain you what is a digital elevation model. Even if you know, but I have to explain everything new. So a digital elevation model DEM is a simple raster where every pixel stores the elevation of the Earth's surface. So instead of recording colored images in an optical image, every cell records the height above the mean sea level. So millions of elevations are combined to form this digital elevation model. Now, the reason why we need a digital elevation model is when the Sentinel-1 measures the Earth's surface, the recorded radar phase contains several errors like it contains the satellite geometry, it contains the terrain elevation, it has the atmospheric effect, it has the ground deformation, it also contains some noise. So here, when we are using the Sentinel-1 for ground deformation, we need to have a terrain so that we will get rid of any kind of errors. So if we don't remove the topographic phase, the interferogram will contain both the terrain effect and the deformation effect, which are mixed together. Now having it done, it will allow the ISCE2 to model the terrain contribution and also remove anything, leaving primarily the deformation signals for the ladder analysis. So without a dam, accurate interferometric processing is not possible. Now thing is, what kind of dam can we use? We have SRTM dam, which is 30 meters. We have ALOS 30 meters. We have Copernicus Global 30 meters of resolution. Here, we'll go for the Copernicus Global 30-meter resolution, which is excellent for the study. So for this tutorial, we are needing to decide which dam to be used. Say, SRTM dam will have some gaps, like they are recorded in block by block. And you are covering a large area, you have to get more number of pieces of dam. So instead, you go for the Copernicus Global 30 meters. You'll get in a single piece. And from there, we will now ask either ISE to download the DEM or we can manually download it from the Copernicus or we can download it from the Alaska site or NASA and use it directly. Okay. Now, I'll ask, I'll command the ISE to download and I'll also show you how to download the um, data or the DEM file from the Copernicus website. So I'll show you how to download this Copernicus Global DEM 30 meters. You go for this here and you can go for the Copernicus data ecosystem or you can also go for the open topography. In any of these things, you can download the data. So you just go for this and then I will go for the open topography. And then here it is easier. So you select a region. Like I told you, I'm going for the state of Nagaland or the northeastern part. So you can just take the data like this and then select a region. So I'm going for this whole Okay, so this is how I selected the area of interest, and from there I can directly go for the geotip format because I want the tip format. Okay, and also you can just leave them like this because there is no need for them right now. Or if you want, you can select these things and you can download them also, and then just have to give your email address. So it will say the request is received, and then it will extract the DEM from the area of interest. You don't have to create any account, you just give the details, and then you'll get the file downloaded. Again, I'm telling you, this depends on the internet speed and the performance of your PC. So I can download this one. After this is downloaded, you can directly paste it in the temp folder, and then we'll go for the next steps. So I have downloaded, and then I moved it to the temp folder, and then I've extracted. So this is the folder, and this is my DEM. So I've copied it outside. So I'm just deleting these files, and here I have this um, DEM. Now, if you want to see, you can just go for ls DEM, and you can see the name output underscore heritage TIF. This is because, see, sometimes when you don't have the DEM file, you need to copy them and then you need to manually paste them in the folder itself. And after that, you have to do the processing and all. Okay. So if you already have the data and the area of study or study of area of interest, you can download and keep the demo also. Or after during the processing, you can go for this Copernicus 30 global, and also you can download it. Okay. So now the dem folder, it is contained in the DEM. The orbit folder contains the orbit files. The SLC folder contains the files here orbits, and you have the SLC. Okay. Now we will start the processing from here. So as we are having this three data sets, one, two, and three, now we'll start the next steps. Now we are going to for the next step, AOI, that is area of interest. The area of interest is you need to understand the geographic location of those places where you want to do the processing. See, all the Sentinel one image covers hundreds of kilometers. Our study area will be very small when compared to the Sentinel one image area. So if you want to go for any particular district or a state, you need to first go for the area details. So you need to, like in Snap, you have that process called subsetting. The same way, if you give the details before, IICET can take that and it will start the processing only to that particular location instead of covering the whole area. So in this step, um, ISCE2 will have a top stack workflow. So in this, ISCE2 will crop the Sentinel-1 burst to the geographical area which we have specified. Instead of processing the complete Sentinel-1 SNC scenes, ISCE2 can only process the data that is inside the bound. So we call it as bounding box. So it has south latitude, north latitude, west longitude, and east longitude. So we need to give the details to the ISCE2. For this, what we can do is we need to use the Google Earth, and then we draw a polygon of the study area, and we need to note the latitude and longitude extensions. Now I'll show you that, and after that we'll continue the processing here. So this area we call it as Paglapahar, which is here in Nagaland between Chumukirima, Dimapur, and Kosima. So this particular area has heavy rainfalls and also heavy rockfall because the poor geology. So this will be my area of interest. So what I'll do is I'll just go for a polygon here and then I'll draw a polygon from say here to space. Okay, so this is just my area of interest. I go for A move I. Now here I need to check the area. So I'm just taking only 32 kilometers perimeter. Okay, so I can just click OK, or you can go for view. I'll show you clearly now. And that. So from this we have to take the corners of this particular area. So out of the whole area, I am asking ISEA to process only this particular area. So that will save the time and also it will reduce the size or the storage capacity and you can get more data easily. If you understand this process once, then you can do the whole thing at a time, or you can just go for the small patches and then you can go for small areas, which would be more easier for you. So here you see the south side, I mean, uh, like the north side, we have one coordinate 25.79, and here you have 25.73, like this. So what we need to do is we create one text file or in the area of interest, we go for the document, say like a new text document, say form 8, everything works, and later we'll direct ISE to take these values from here. So I say south is 25.73, 5.81 west into so we'll just save it like this, and then we inform ISE2 about this text file. Now we have the Sentinel-1 zip file here, and then we have the orbits, we have the DEF, and we have the area of interest. Now we start the running of the step 5. I mean the next stage. So in the step 1, step 2, step 3, step 4. And for the step 5, we are going to do the actual processing part. So please let me know if you have any queries, and then I'll reply the comment.